Okay, it's working now, sorry. Welcome to Tutte Colloquium, and we are very happy to have Barak to give the talk today. So Boaz received his PhD degree from Weiz's Institute of Science in 2004. And then afterwards, he worked in Microsoft Research and also in the computer science department of Princeton. And now he's Gordon McKay Professor of Computer Science at Harvard. Boaz works in different areas in theoretical computer science, in particular the algorithms and complexity theory and cryptography. And today he's going to talk about generalization bounds for rational self-supervised learning algorithms. Boaz.
Thank you very much. So, yes, an alternative title for this talk, which maybe you'll see why I think it might make sense, is whether understanding generalization requires rethinking deep learning. And this is a joint work with two amazing students, Yamini Bansal and Gal Kaplun, who are actually here. So if I mess up too badly and I start making nonsense at all, Yamini and Gal, feel free to cut in and correct me. And okay, so we'll see this talk will be some mixture of both theoretical results and some proofs as well. And please do feel free to stop me at any point and ask questions. Okay, so the basic setting we are in is a setting of supervised learning. So in supervised learning, the way to think about it is that we have data. So we'll think of a classification task. So we have these the data points x1 till xn, and they have some labels, y1 till yn. You can think of yi as either, say, +1 or -1, or some other, say, 1 of 10 labels, or anything other than that. You can think of it abstractly for now. So we have a training procedure, which basically takes this data and then spits out a classifier, which is some function f that takes the data domain x into the label domain y. And the hope is that this classifier is going to classify correctly future points that we have not yet seen. So typically we define two quantities. One quantity is the training accuracy. This is the probability that this classifier outputs the right label on a random point in the training set. And the probability here, we'll think of it as expected probability. So think of it probability over the data points, probability of any randomness that is used by this training procedure, and the choice of I in n, the index of the training sample. And the second thing is the test accuracy. This is the probability that f of x equals y on some fresh xy that come from some distribution d. Okay, so so far we have been very, very abstract. This is just a generic way to talk about any type of supervised learning, no matter whether it's using a linear classifier or deep learning or anything else. So and one quantity that we will be interested in today is the generalization gap, which is the difference between the training accuracy and the testing accuracy. So typically in statistics, we want an empirical quantity and a quantity we can measure, like the training accuracy, to be close to the quantity we care about, which is the testing accuracy, the probability that we'll classify correctly over future examples that we have not yet seen. Okay, so so this is the setup, and let me kind of give an example what people do today with deep networks. So, you know, if you look at the most important problem in the world, which is to classify images of dogs versus cats, then how do you solve this problem using a neural network? So you think of these images as some vectors, right? They live in some high dimensional space. So you think of these images as vectors in some Rn. And then what is, you're given these images with the labels. You say, okay, this is a dog, this is a cat, this is a dog, this is a cat. And what a neural network is really basically, you just do a curve fitting, right? So you find some very complex curve or hyperplane that separates out the dogs from the cats, right? So the dogs will be on this side, the cats will be on this side of the curve, and that's how you classify. And what you hope is that this curve that fit the training data will also fit future test data. And indeed, this is successful. This is not necessarily, I'm just giving here some examples. This is not the state of the art. They are like, but they're even in CFAR 10, there are like things that get, I don't know, 98% or something like that. I'm not, never keep up with exactly the right numbers, but you get pretty good performance. And you succeed with, you succeed with this type of approach. You can succeed with, you know, very, very good performance, you know, high 80s, and sometimes even mid or high 90%. So you can get very good performance. Interestingly, these, the current neural networks that people use are very complex in sense of having many, many parameters. And because they have enough parameters, so they can fit the cats and dogs perfectly. So you will notice that the training accuracy is always 100% in all of those cases. But the testing accuracy is still close to 100%, but you know, it's still very good, but not 100% and not even necessarily that close to it. And the question is, that people asked is the training accuracy any indicator of the testing accuracy? And there was a very beautiful paper who basically said, no, the answer is no. And this was a paper by Zhang et al. And what they showed is the following. They had a very clever experiment, which essentially said the following thing. Suppose we just give you, we'll just consider a different distribution where we still use the same images, but we, instead of choosing, you know, instead of labeling them correctly, a dog is a dog and a cat is a cat, and in that case, there are like 10 classes, so in case, instead of labeling these 10 classes correctly, we will label the 10 classes completely randomly. So every time we choose one of the 10 categories completely at random. Because we choose the category completely at random, you cannot get better than chance success in the test. So this is clear that you'll not get better than 10%. But what was surprising is that you actually do not get, you still get 100% in the training, which means that basically if you, it shows that there is a huge gap. So in some sense, if you got 100% on the training, it doesn't tell you anything. You could be performing 92% of the test, you could be performing 10% of the test. So training performance by itself gives no indication of your future performance on samples that you have not seen. And this has, you know, this is a part of a whole research agenda on trying to understand that and when could you do that. But in some sense, the bottom line is that supervised deep learning is really wonderful. It works really well in practice. And, but by its own, the training accuracy is not informative. Just looking at performance on the data set doesn't tell you on its own anything on what will be performance on future samples, even if they come from the same distribution. And for this reason, the Zhang et al. Titled their paper, Understanding Deep Learning Requires Rethinking Generalization. So typically in statistical learning theory, we really think of the following thing. We think that we want something that, you know, train minus test should go to 0 as n goes to infinity. And we so the natural things would have been to say, okay, we have some quantity like 100% versus 92%, and it can go to zero as kind of n goes to infinity, and the gap, sorry, the gap would go to zero as n goes to infinity. But we kind of see that this is not really the right way to think about it, because somehow training for these networks is kind of permanently stuck at 100%, and regardless whether they are great or terrible. And in this work, we look at a different version of deep learning, that one that we did not invent. This is a method that people have been using a lot in natural language processing, and more recently also in vision tasks. And we give it the name of self-supervised plus simple, and we'll explain exactly what it is in a slide. And we show that these algorithms both still work great in practice, and this was known before. This, although not, when I say before, it's like known since this year that it also works for vision tasks and works great. It's still slightly less than the supervised deep learning, but getting there. But what we show is that in these algorithms, they all actually do have a small generalization gap. And in fact, we can prove that they have small generalization gap. So, so in some sense, we say maybe the title should be changed. Maybe the problem wasn't with generalization, but rather the problem was with this supervised deep learning. If you just don't use supervised deep learning, but you use these self-supervised plus simple algorithms, these SSS algorithms, then you don't have this issue of generalization gap being large and training accuracy being a non-informative signal. So, so maybe it's not that we were doing generalization wrong, it's that we were doing deep learning wrong. But of course, this is up to interpretation, and regardless, the result is just a generalization gap for these SSS algorithms. So I guess at this point, I'm still at a very kind of high level, but before I start to get more technical, are there any questions at this point? So since everyone has their videos off, I cannot see if people are nodding or not nodding, or nodding off, but I'll just continue. Please, yeah, do feel free to stop me and ask a question at any time if a question arises. Okay. So let me define what is self-supervised plus simple algorithms, SSS algorithms. And the name, we gave it the name, but this thing has been, like I said, has been in various results, both in NLP and in vision, but let me be precise about what we mean. So one way to try to think about it is to contrast what we've seen in standard, which I'll call end-to-end supervised deep learning, versus how a baby learns how to distinguish between a dog and a cat. So basically, as we said, like standard supervised learning, I call it end-to-end because you basically, you get you do it in kind of one piece. You fit a very complex curve to fit your data, and you fit it, as we've seen, to fit 100% of the data. So you get a bunch of samples that are labeled cat, dog, cat, dog, cat, dog, and you fit a curve that separates all the dogs from all the cats, and then you use that to make future predictions. But if you compare how a baby learns to distinguish between dog and cat, that really doesn't happen like that. What a baby will do is the following. A baby will see all sorts of images that throughout their life, say the first year of their life, and these images will not be labeled. These will be unlabeled images. And in some sense, you could probably count even before the baby was born, the visual system in the brain has been evolved through observations of many unlabeled images throughout evolution. So it has evolved through seeing many unlabeled images. And after seeing so many unlabeled images, you usually my kids are kind of old, but as far as I remember, you don't really have to spend a lot of time to explain to them what is a cat and what is a dog. You show them one example, okay, this is a cat, this is a dog, and next time they will see another cat and another dog, even if they don't, come even from the same distribution, they look a little bit different, they will still, most of the time, they will know how to say, if it's a cat or a dog. So, and SSS algorithms are just a little bit more along the lines of, they are just a little bit more along the lines of these kind of, approach than the standard supervised learning. So the idea is the following. So an SSS algorithm first takes a lot of unlabeled images, and it learns a representation of these images. So it learns some way to represent these images. So we can think of a representation as some map that takes these images from the pixel space to some representation space. You can think of it as another like high dimension space over the reals or whatever it is. You typically think of it as abstractly in this talk. So, so the representation you learn by only observing unlabeled images. And then what typically we still often don't know how to still do it with only one cat and one dog, but then we get some, what happens is that if you look at the cats and the dogs, what happens to them in this representation is that the representation is somewhat nicer. So in this new space, you don't need a complex curve to separate out the cats and the dogs. You can do that by a very simple classifier. So for example, maybe a linear classifier. So basically the idea is you learn a very good representation on images, and in this good representation, maybe the semantic classes become linearly separable, or some other way that you don't need a complex classifier anymore. And so this is the idea of an SSS algorithm. It has two stages. One stage where it gets all the data without the labels, and then another stage where it fits a simple classifier to the representation of the data that it learned in the first stage and the labels. So here is it a little bit more formally. And we are going to be in typically the motivation that people use the motivation that people use these kind of things in practice is because, of course, they really love to be able to use, unlabeled images. But we are going to analyze it in the same setting as standard supervised learning. So there are no unlabeled images. There is a training set that contains images and their labels. It's just that we're going to use it in two different stages. So in the first stage, we are going to only use only the data without the labels. And so we have some procedure that outputs a representation. And this representation can be very complex. So it can use more parameters than the data. In principle, it could memorize the entire, all the data that it has seen. This can be a very complex representation, very nonlinear representation. In fact, it should be. And then the second stage is we take the representation of our data, so R of x1, R of x2, etc., and now we fit a simple classifier. So this classifier should be simple. So this is what an SSS algorithm. So this is basically the definition of an SSS algorithm. So it has two stages. One stage learns a complex representation, but without looking at the labels. And the second stage learns, fits a simple classifier using the labels. So any questions about the definition of what is an SSS algorithm? Okay, so I'll continue. So how do these SSS algorithms do? So it turns out they do also pretty well. So these are some very, very recent kind of top of the line SSS algorithm that people have been using. So they typically use some architecture that's very similar to the architectures we have seen for classification. So the complex part, the representation, is basically built on top of the same type of architecture, and then we put a linear classifier on top. And these, and they achieve decent, decent results. Interestingly, and we already see here a slight hint that maybe things are different, they often don't achieve 100%. So unlike end-to-end supervised learning, they typically don't achieve 100%. And indeed, if you run the same experiment, if you run the same experiment that Zang et al. Did on these classifiers, you see that they're training, when you make everything noise, when you add noise, you basically make all the labels random. Test obviously will drop to 10%. That's necessary. But what's interesting is that training probability accuracy will drop as well. So here we see that actually, training performance is informative. So basically, even though these are algorithms that have similar performance to end-to-end supervised learning, but unlike end-to-end supervised learning, you can actually learn something about their test performance from their training performance. And we'll see that there is a reason for that we can actually prove that this is the case under some assumptions.
Boaz?
Yes.
This is with only training the last layer, not fine-tuning.
No, this is a simple fit. So you're just, you're just using a simple linear classifier. You're not
right.
fine-tuning the entire, like the representation is fixed.
If you fine-tune, it's probably back to garbage like before.
It should be, I didn't try it, but it should be basically back to, because you could get 100%. If you fine tune for, invest enough time with it, you can get 100% training accuracy. So this is when you do just a linear fit or another simple fit. I think in these 3 experiments that we're talking about, it's just linear, but yes. But interestingly, you don't need to fine tune to get very, very good test results. You can, get an extra percentage or something like that if you do fine tune, but you don't, but you can get pretty good without that. And we actually ran in this an experiment that maybe, that interpolates between these 2 cases. So this is basically, this is 0% noise. And this is 100% noise. Or maybe, let's say maybe 90% noise, like 90% of the labels are wrong. And of course, that basically means that it's all random. And we actually ran this experiment where we interpolate between the 2 extremes. And I think it's somewhat instructive. So this is what happens if you start increasing the level of noise. So you see on the left, you have the supervised. So on the left, you have the supervised algorithm, the end-to-end supervised algorithm, and their training performance is always 100%. Maybe I see here like it sometimes dips slightly below. So their training performance is always 100%. And the test performance just drops and drops as you add more noise. If you look at these SSS algorithms, they never actually get very far between train and test performance. So train is actually a very good indication of test performance for these SSS algorithms. So they do actually have a fairly small generalization gap. And this is basically what we want to prove now. So this is the empirical thing. So the empirical thing that you observe, this is, this is big and this is small. And what we now want to do is to prove that this is small under some assumptions. And there has been some work that proves that things along these lines are small under some incomparable assumptions, including work by Aurora et al. And work by Jason. But I'll focus on, but we're using incomparable assumptions, so I'm not going to discuss them. But this is a very active area of research. Indeed, I think these works that are really things that just came out. So, okay, so we want to look at the generalization gap of supervised and SSS algorithms. So both of them can be abstracted as just this box that takes data and outputs a classifier. And the generalization gap, one way to think about it is, yes, you can look at the probability that it's correct on xi, and subtract and compare that. So this is right. So this is train, and this is test. Probability that is correct on x for fresh x. And so if you look at this generalization gap, we are now going to define some quantities that refer to this experiment. So kind of motivated by this noisy experiment, we are going to look at some quantities that refer to the experiment where we noise, say, 5% of the labels. So let's say 5% of the labels, we flip their, we're going to flip their, we're going to flip the label and feed it to the training procedure, feed a wrong label, a wrong that's chosen at random from some of the other classes. So now I'm going to define the following quantities. So first of all, I define a quantity I call the correctness gap. So this is basically you compare the training accuracy versus the training accuracy in the noisy experiment. So this is how much did the training accuracy deteriorate when you added noise. And there is an important caveat here is that the way I define it correct means that correct, I mean correct with respect to the original label. So, so for example, if I had, I had 50 dogs and 50 cats, and let's say I took 5 of them and I flipped them, I still ask the class, I still try to estimate what's the probability that the classifier gives me the correct answer, which means the original label, not the ones that that it was trained under. So, if it's a classifier that training accuracy in the first, in the sense that it always fits the labels, it's 100%, then the robustness gap will be 5% because it will recover the original labels for those things where it wasn't corrupted. We now define another quantity which we'll call the rationality gap, and this is the performance on. So this is we subtract the following quantities. This is basically the training in the noisy experiment, but we look only on those labels that were received corrupted labels. So the idea in this experiment, right, we had, so in this experiment, we had the original data and we corrupted some of it. We gave wrong labels and we measure now performance here just on the noisy. And we compare that with performance on completely fresh X that we didn't get any label at all. So it's basically ask what is better to get to, if I give you an image of a dog and I tell you that it's a cat, are you more likely to guess that it is a dog than if I give you this image and tell you nothing? And if you're rational, if I tell you that something is a cat, it's more likely to think that you will be more likely to think that it is a cat. So if you're rational, then this should be less than 0. And indeed, sometimes when we define rationality gap, we'll actually think of the maximum between 0 and this. So basically, this can often be negative. So intuitively, it should be negative, but so we'll kind of define the maximum between 0 and this. And the first the third thing we'll do is define a memorization gap, which basically it compares the probability, the overall training accuracy under the noisy experiment, and you subtract the accuracy on those things which got corrupted. And again, accuracy with respect to the original uncorrupted labels, accuracy on those corrupted things. And we think of it as a memorization because it is going to be very large if you are completely incorrect on the things that are, you got the wrong label. And now if you look at these things, you'll see that some terms appear several times. So you see this term appears here and here, and here, and this term appears here and here. So if you add up these terms, you actually get the generalization gap. And because we took the maximum between this and 0, so basically what we get is, right, so the rationalization gap is the ability to memorize the wrong label. And what we get is that the generalization gap is smaller than the sum of memorization, rationality, and robustness. And yeah, we usually write it in the other way around, RRM. So yes, so we call this the RRM bound. So generalization gap, and this is always true. The generalization gap is always at most the memorization plus rationality plus robustness. The only question is whether it's interesting. So this is this RRM bound. And to get a sense for that, let's kind of go through two examples. So one example is an interpolating network. So an interpolating network is one that fits perfectly all the labels that it was given. In this case, the test accuracy is whatever it is. It's some P. And the probability that if you didn't corrupt any labels, you get 100% train accuracy. If you do corrupt some labels, then you'll get 95% train accuracy. You will be perfectly right on the things that you got the right label and perfectly wrong on the things that you got the wrong label. So the robustness gap will be 5%. And now if you look at the probability, the probability that you're correct on the noisy examples will be 0 because you'll be perfectly wrong there. That's because of interpolation. So you get that rationality is going to be 0 minus P. So this is going to be smaller than 0. Smaller, not subset of. And memorization is going to be 95%. So for an interpolating network, we see that robustness and rationality will be small and memorization will be large. And in this case, the RM bound is kind of trivial just because memorization is such a large term that it basically is meaningless. And let's now look at, so is this example clear? Any questions about it? Okay, so I'll continue. So another question here is kind of a very degenerate or pathological example. So suppose that the data is really, really easy to separate. It's like linearly separable to 10 classes. So it's very, very easy to find. You can think of the data maybe is just, you know, there are 10 classes and the data is always just the standard basis vector, something like ridiculous like that. There are some 10 orthogonal directions that determine it. So think of the following silly representation. So R of X outputs X if X is in the train set and 0 otherwise. So this is a very kind of complex representation because it needs to memorize the entire train set, but this is okay. We are allowing very complex representations in SSS algorithms. And think of the classifier as basically just finding the best linear separator. So right, so in this case, if we look at a fresh X that's not in the training set, then we will just output nothing. Our representation is meaningless there. So we will not do better than chance. So our test accuracy will be not better than chance. So it will only be 10%. On the other hand, our train accuracy will be 100% because for the train set, the data is linearly separable. We are going to separate it completely. The probability that we are going to correct, even if there is 5% noise, is still going to be 100% because of the self-correcting properties of linear separability. So we will find the right linear separator, and then that right linear separator will be robust to this 5% noise. So so the robustness gap is 0. Even on the noisy things will still be correct because of linearly separable. So that means that rationality here is very large, right? So rationality, which we supposed to be negative, is actually very large positive number. So it's and memorization is going to be 0. There is no gap. There's not going to be any gap between what we do on the noise and what we do on the overall train set. So in this case, the memorization is small, the robustness is small, but rationality is large. And again, RM bound is trivial in this case. But notice that we have done something that's very silly. We have kind of deliberately tried to make ourselves behave badly on, we have deliberately tried to ensure that we behave badly on things that we have not seen before. So we've done kind of the opposite thing which you're supposed to try to do when you're learning. And indeed, we can prove this kind of theorem that if you have a large rationality gap, it's always because you're being stupid. In the following sense that whenever you have a large rationality gap, there is room to increase your performance. And I'm not going to go into the details of the proof, but the idea is that you can always replace no label with a random label. But I would just say that this is really a theoretician's proof, because the procedure B will still be polynomial time, but it will be very expensive, because it basically will mean every time you get you need to make inference, you need to make a decision about a new sample, you have to kind of redo all of your training from in advance. So this is not something you would actually want to do, but it's just kind of a proof of concept that rationality ought not to be, it's supposed to be close to zero, unless you're really leaving kind of performance on the table. Okay, so basically the bottom line is that we have reasons to believe that rationality should be small. We have also, should be roughly zero. We also have some reasons to believe that robustness should be small. So let's see how it looks in kind of practice. So in practice, we see that typically robustness is small. So it's, typically it's less than 5%. Rationality is small, less than even 1%. And memorization, that's the thing that, so just notice here, here it's very negative for some things, but it's always smaller than 1%. So rationality is always small, sometimes very negative, but it's always small. And memorization is interesting because memorization is typically small for these SSS types of algorithm, and large for these end-to-end supervised algorithms. So memorization is really the part that seems to distinguish between the algorithms that have large generalization gap and algorithms that have a small generalization gap. So robustness and rationality are always small, and memorization is sometimes large and sometimes small. And the main theoretical result is that we can actually prove it. We can actually prove a bound on the memorization gap of these SSS algorithms. And the theorem is the following. So for every SSS algorithm that learns a representation R and then fits a classifier G, the memorization gap is at most O of square root of the complexity of G divided by N. So the complexity of G, the formal definition is in the paper, which will come out on arXiv next week. But for this talk, you can think of the complexity of G as the number of bits that it takes to describe G. And the main thing is that it doesn't matter how complex this representation are. So this is independent. So this could be very complex. It doesn't matter how many parameters you use for the representation, as long as your classifier has, it can be described by, say, little o of n bits, then the memorization gap is going to 0. So now let's see, so now let's outline the proof. So we have these two, again, these two phases. This is how an SSS algorithm looks like. And to restate this, we think of the following. So let's just, throughout the proof, let's just kind of fix, X and Y. Randomness in this experiment comes from the choice of randomness in these. So we'll also fix R. So we'll kind of fix everything that happens up to this stage. And here there is randomness that comes from noise, and randomness that comes from the coins maybe of this fitting algorithm. So we define G, which is the classifier that the simple classifier that we find. So this is a random variable, and And what we're going to prove is that the memorization gap, which is the, it's the difference between, this is the training accuracy. This is, right, the training accuracy in the noisy experiment. So this is, we are all going to be always in the noisy experiment. So this is the noisy training accuracy. And this is the training accuracy on the noisy, on those samples xi, such that yi is different from the label that you were given. So this is the memorization gap, and we are going to show that this is at most O of the square root of the entropy of G divided by N. The entropy of G is obviously upper bounded by the number of bits it takes to describe G, so that will prove the statement. So this is what we want to prove. And here is how we're going to prove it. So we're going to define two random variables, two Bernoulli 0, 1 random variables over all the randomness here and the choice of a random index I. So A is the probability is 1 if the prediction is correct and 0 otherwise. And B is 1 if the label is incorrect and 0 otherwise. So this thing that's written there, this memorization gap, we can think of it as it's the expectation of A minus the expectation of A condition on B equals 1. So this is this. So we need to bound this difference, the difference between the expectation of A and the difference between the conditional expectation of A. And by some kind of a pin-square inequality, which I'm not going to, by some use of the pin-square inequality, then basically it will be enough to show that the mutual information between A and B is at most h of G over N. So that will be enough to derive the bound that we need. And intuitively, you can see that if there are small mutual information, then conditioning on B is not going to change much the expectation of A. And so you can trust me that the math works out. Okay, so how do we prove that? So the idea is the following. So we take, we write a quantity n times this mutual information, and we just expand according to the definition. It's h of b minus h h of b minus h of, I think actually I got this. It's not going to matter, but I think it's actually the other way around. And the reason it's not going to matter is the following. So the idea is the following. So I claim that this is an inequality. And why is this an inequality? The reason is that B is simply going to be 1 with probability, say 5%, and 0 with probability 95%. And it's not going to matter. This is always how B is going to look like, no matter what the index is. So here, this is just h of B. And you're subtracting a quantity where you sum up over all conditionings of J. So that generally will reduce entropy. So you're subtracting a smaller quantity, so you're getting a bigger thing. So this is why this is an inequality. And this is basically just the mutual information, the conditional mutual information. So because we had a factor n here, so here we just get that this is the conditional mutual information. So what we got is that n times the mutual information between A and B is smaller or equal than the sum over all j from 1 to n of the mutual information between A and B conditioned on the index I equaling j. And now there is only, if you know the classifier G, then you know all the predictions and you know if they are correct or not. So we can replace A with G. And then we can use the fact that these B1 till Bn are just IID random variables to say that this is less than the mutual information between G and B1 till Bn. And this is, of course, less than the entropy of G. So I might have sped a little bit through this derivation, but if you go through it slowly, it ends up working out. And in the actual paper, we actually look at a more refined quantity that is that we can actually empirically estimate for actual, so we define the complexity in a more refined way that we can actually empirically estimate. And then what we actually get in practice is the following. So let's just look at examples. So this is, we took a bunch of different SSS algorithms of various generalization gaps. And this is the plot of the generalization gap. This is just the plot. This is the line x equals y. It just scaled differently. So this is basically, we just, a blue dot here correspond to one example that we ran of some some SSS algorithm that has a certain generalization gap ranging from 1% to almost 15%. And now we looked at what's the memorization gap of these classifiers. So one nice thing that we can already see is that the memorization gap really does explain, in most cases, the bulk of the generalization gap, especially when the generalization gap is big. So, so the memorization gap is really the thing that kind of explains the most. And then we looked at the rationality gap. The rationality gap sometimes can be, most of the time it's 0, but sometimes even if it's not 0, it's fairly small. I think only in some extreme cases it was up to 4%, but usually it's like only 1%. And then if you look at the robustness gap, that's also fairly small. In fact, it's even smaller than the 5% that you could, that you typically see. And there are sometimes you can prove that it's small, although that requires its own set of assumptions. And now if we use our theorem and replace the memorization gap by the bound, this is the RRM bound. So the RRM bound, the nice thing that you can see is that it's close to tight. It's not exactly the generalization gap, but it's not that far from it either, which is nice. And if we replace the memorization by the complexity upper bound, we get bounds that are not tight, but they are often non-vacuous. So, so often they are like under 100%. And in fact, sometimes they are actually pretty good. You see, sometimes they're even like 10, 15%. But now getting under 100% might not seem like very impressive to anyone except someone that have actually tried to do generalization bounding for practical things, because often it's very hard to get generalization gaps that are under 100% or under, that are non-vacuous, that are less than the difference between the test and between 100% train and the test performance. So it is actually quite interesting that you get like non-vacuous generalization gaps. And that's basically it. I think I'm probably already brushing up against the time limit. So there are tons of open questions raised by this work. So I think this work shows practitioners somehow, I think, already know that SSS algorithms are good for various reasons, but this work shows that there are also theoretical reasons to like them. And for rationality, we have this performance on the table theorem, but it would be nice to also actually give rigorous bounds on the rationality. I think that could be hard. For robustness, there have been some works, but not as many as initially I was sure that I will stumble into, so that we will stumble into a whole treasure box of literature on robustness. But so far we have seen some bounds, but not as many as we wanted. And yeah, this notion of what does it mean to have a good representation, that's a whole different thing. And we completely abstract it, but yeah, right now people do it in various ad hoc manners. Sometimes they say, representation allows you to reconstruct half of the image from the other. Sometimes they say it allows you to push away distinct images and push together the images that are nearby. And yeah, and the final question is maybe when you do supervised learning, and some people have this intuition that maybe what really is going under the hood is that you are actually doing SSS algorithm. And that's why actually, and maybe that's a way to explain what's going on in supervised learning, is that under the hood, what's going on is that you are actually learning a representation and then fitting a classifier on top of that. But this is kind of quite speculative. So with that, let me finish and see if there are any questions.
Thank you, Boaz. So any questions for Boaz?
Hi, this is Steve Avastis. Can you hear me?
Yes.
Hi. So you cited a paper near the beginning of your talk that had 5 authors to motivate the generalization gap.
Mm-hmm.
But I recall there was another paper that came out about 6 months later by a different group of 5 or 6 authors. Oops, sorry, dog barking. That tried to that said that the original paper was asking the wrong question, and they asked a different question and then came out with an affirmative answer about generalization. But I don't remember this exactly what question that second paper had. Do you know what I'm talking about?
So I'm not sure, but I think Jason is here, and I think he would actually probably know more than me what is this.
Sorry, I missed the first 10 minutes. So what was the original paper?
The rethinking generalization. I think the paper that shows that rethinking, so the paper that somehow showed that a lot of classical methods will fail to give generalization gap. There is also, that's not the only work of that type. There are also some works by Misha Belkin that also kind of show barriers to proving generalization bounds. But I don't know, Steve was saying that there was like another paper by like 5 authors that said that this rethinking generalization was actually asking the wrong question or getting the wrong answer.
So a paper after.
Yeah, it was by Joshua Bengio, and was one of the authors of that second paper, and Simon Lacoste Julien was another, and there were about 5, 6 other authors on that paper. And they said they redid the experiments, and they said, well, those guys didn't quite ask the right question, and here's what they should have done, or something like that.
I don't think I know this one.
Okay.
Just wondering, yeah. Okay, thank you. Yeah.
Yeah. So I'm going to look it up after the talk, and I'll see. I'll just I don't know it myself. Of course, that paper is just a motivation for what we are doing. I mean, our results don't rely on that paper in any way, and I think. Even if we had good generalization bounds for these end-to-end supervised algorithm, it would still be interesting to find a generalization bound for SSS algorithms.
Okay, other questions?
Mm-hmm.
Well, maybe I can ask one. So in the very early slides, you mentioned this so the generalization error increases when you add noise to the training set, right?
Mm-hmm.
I just wonder if the generalization error exhibits some kind of phase transition as the function of the noise for a large set of samples. From your sliding, the picture that you slide, it seems like a smooth function, but I just wonder if it's the case or not.
So it seems that it doesn't, like in the sense that for supervised, for supervised learning, like end-to-end supervised learning, what you have is that if you look at train accuracy, it's just a flat line at 100%.
Mm-hmm.
And if you look at test accuracy, then it starts at whatever, 92% or whatever the performance they get. And it kind of, sort of more or less kind of linearly decreases all the way to 10%, the trivial, what you get by chance. And if you look at, oops. Okay. And if you look at and if you look at the SSS, then basically you get, say, if you get a good SSS similars, and maybe you get 92 and 96, and they kind of decrease more or less together. Like, it's not completely linear, but it's a kind of decrease together.
Okay.
Yeah, in some sense, they need to meet. I think when they get to, no, they actually don't need to meet. They actually make whatever.
Yeah, I feel that the concept of the generalization error is trying to, to say how the error in the test in the training set matches to the error in reality or in more general set. But the example where you add noise seems to particularly fool this the supervised learning, because you define the error in the training set to be the probability that it gets correct, right? And I think the correct is defined by correct according to you shuffled the label already. For instance, if you actually really define correct to be correct as what the category it's supposed to be, do you still see such figure like that?
Right, so they would be more complicated, but the way to try to think about it is that we simply define a different probability distribution. So what they basically, this Zangetol, and maybe that was possibly this kind of, I could imagine that this might be the kind of criticism that someone would have, and maybe that's that paper, I don't know, but yes, sorry, just a second. I could imagine that this is the kind of, but basically what the way to try to think about what they did is that there is a probability distribution, and they, generally probability distribution could be anything of the form X, Y. And what the Zangetol did is they made the X natural, so at least the X is natural, and they made the Y not so natural. So the Y, instead of being, so the Y, instead of having the typical Y, which is the right class, now the Y, Y condition on X is, random with probability 1 minus, with probability some eta, where eta is the noise, and the original, f of x otherwise. So it's a probability distribution, and you can define with respect to this probability distribution both the training accuracy and the testing accuracy, and that's the way you can look. And then you can come up with other probability distributions that are trying to, you can try to find the other probability distribution that will try to catch to try to approach the same type of the same phenomenon, but.
Thank you.
It doesn't have to be, again, like these were more motivation that in a sense that than anything that we technically need for the result.
Understand. Thank you. Other questions?
I have another question here.
Yes.
I assume that here the label is supposed to be unique, that an image can either only be a cat or a dog. So in the case when we allow some more complexity, say we allow list decoding, like there are 600 possible animals, and we do not necessarily want to classify them according to the species, but like we just want to say that sometimes we know that it is an actual cat. Sometimes we just know that it is probably one of the fish, versus it is a bird, or it's actually one of the ducks. How much does it complicate the learning algorithms?
Yeah, so I think the learning algorithms themselves, you could try to, this is, so learning algorithms themselves, they have, people have looked at this for learning. I personally, we did not look at all these kind of cases where you have hierarchical classes. Generally, empirically, I can say that our bounds become these proven bounds. So this is basically, this table is for CFAR10, but we also ran this thing for ImageNet that has many more classes, and our bound both deteriorates and also becomes more computationally intensive to actually evaluate. So we do have some non-vacuous things also for ImageNet, but it becomes, they become weaker and become more computationally expensive to evaluate. And if you had, if you had even more, if you had even more classes, then it would be even worse. And generally, our whole theory right now assumes that the correctness is, is about getting the exact label. You either get it correct or not. We didn't think about, other type of things. So it's hard for me offhand to know, do things easily generalize, or are there like huge landmines there? So I don't know. But I do know that our result, the O term hides a term that depends on the number of classes. So there is some hidden term there that could grow.
Thank you.
Or more accurately, maybe, it's more or less a term that could grow in practice with the number of classes.
Okay, maybe just last call of questions, if there's any. If not, let's just thank Boaz Barak for this nice talk.
Thank you.
Thank you very much.
Thank you. I
Yeah.
hope at some point to be able to come